Right, so this is lesson 7, linear and quadratic systems. Our essential question is, how can you solve a system of two equations or inequalities in which one is linear and one is quadratic? Okay, here's our table of contents. Determine the number of solutions. When you have a quadratic and a linear equation, you can have three options for finding solutions. You'll either have two solutions, so 2 points where the linear equation crosses the quadratic, one solution where the linear equation will touch the quadratic at one point, or no solution where the quadratic and the linear equation never touch. Determine the number of solutions. How many real solutions does the system have? X squared minus 3 and x plus 3. So x squared minus 3 is our quadratic formula. X plus 3 is our linear. So the first thing we want to do is graph our equation. So we're going to graph the quadratic first, x squared minus 3. Then we're going to graph our linear equation at x plus 3. And you can see that there are 2 points where we have contact. So those are the 2 points where the function intersects and they have two real solutions. So in this case, it looks like x equals 2, negative 2, and x equals positive 3. So those are the two solutions. So I have x equals negative 2 and x equals positive 3. You can also set these equal to each other, which we're going to talk about in a second, and solve them to get the same solutions. Solve a linear quadratic system using substitution. How can you use substitution to solve y equals 2x squared minus 6x minus 8 and 2x minus y equals 16? So again, I have a quadratic and I have a linear function. My first step is going to be to substitute the values of the first equation into the second equation for y. So I'm taking this second equation here, this 2x minus y equals 16, right? And I'm taking my first equation where y equals 2x squared minus 6x minus 8, and I'm substituting that entire first equation in for my value for y. Okay. I can then simplify the equation by factoring the negative sign and combining like terms. So I factor this negative sign, so I get negative 2x squared plus 6x plus 8. I combine my like terms. 2x and 6x are the same, so I add them together. So I get negative 2x squared plus 8x plus 8. I can then factor out a negative 2 and divide both sides by negative 2. So that gives me x squared minus 4x minus 4 equals negative 8. Okay. Then I can continue solving for the x value by factoring. Okay. So I have x squared minus 4x minus 4 equals negative 8. I get x squared. I move the negative 8 to the other side. X squared minus 4x minus 4 plus 8. That combines to give me a positive 4. Well, that's the same as x minus 2 squared. It's a perfect square trinomial. So I get x minus 2 equals 0. So my x equals 2. I can substitute the value of x equals 2 back into one of my equations. I'm going to use y equals 2x squared minus 6x minus 8. And I'm going to solve for y. So my y equals negative 12. So in this case, there is only one solution. When we found our x equals 2, it showed us that there was only one solution. It's called a multiplicity. So at that point, the equation's only going to touch, they're only going to touch each other one time. And it's called a tangent. How can you use substitution to solve negative 3x squared plus x plus 4 and 4x minus y equals 2? Again, I have y equals, so I'm going to substitute that value for the first equation into my second equation. I'm going to simplify the equation by factoring the negative sign and then combining my like terms. So I get 3x squared plus 3x minus 4 equals 2. I can then solve by factoring 3x squared plus 3x minus 6, I take out a 3 from all of that, so I get 3 times x squared plus x minus 2. X squared plus x minus 2 does factor into x plus 2 times x minus 1. Okay. I set each of those factors equal to 0, and I solve. So x plus 2 equals 0, so x equals -2, and x minus 1 equals 0, so x equals 1. In this case, I have two real solutions. I substitute both of those values into one of my equations. So I solve -2 first in for x. I solve for y, I get -10. And I substitute 1 in, I get -2. So my two solutions are 1, -2, and -2, -10. So when x equals 1, y equals -2, and when x equals -2, y equals -10. Okay. Applying a linear quadratic system. Yusuf kicks a ball up a hill for his dog Zara. The hill is modeled by a line through the origin. The path of the ball is modeled by the quadratic function shown. How far does the ball travel horizontally? How far must Zara run up the hill to catch it? So the first thing I want to do is actually set up these two equations. I have a quadratic function. I have a linear function. The second is to substitute the value of the second equation into the first equation for y. So basically, I'm setting them equal to each other since they both equal y equals. I then simplify by moving all the values to one side. Okay, so I have -2x squared plus 8x equals 0. I can factor out a -2x. So I have -2x and x minus 4 equals 0. I set each of those factors equal to 0 and I solve. So I get x equals 4 or 0 and x equals 4. With that being said, those values make sense because I'm starting at the origin of my graph. So at 0, 0, it would make sense that x equals 0 is one of my solutions. I then substitute my value of 4 in for x and solve. So I get y equals 2. That information is going to be helpful because I'm finding how far the ball traveled horizontally, which I did with x equals 4. That's my horizontal distance. But I also need to find how far Zara ran up the hill to catch it. And in order to do that, I'm going to use my horizontal and my vertical heights to figure out my hypotenuse for my triangle. So I find the hypotenuse of the triangle to find the distance that Zara runs up the hill. So my A value or my horizontal distance is that 4 feet. My B value is my vertical distance, which was 2 feet, which we found when we substituted that value of 4 into our equation and found my value for y. Okay, so to find the hypotenuse, that's a squared plus b squared, and then the square root of that. So 4 squared plus 2 squared is 16 plus 8. 16 plus 8 gives me 24. The square root of 24 is 4.9 feet. And we're only dealing with the positive in this case because really when I take the square root of something, I would get plus or minus 4.9 feet. But again, I'm dealing with distance, and distance is always positive. Solve a linear quadratic system of inequalities. So this is very similar to how I solve the system of equations. So now I'm dealing with inequalities. I have y is less than -2x squared plus 8.5x, and y is greater than 4x 2.
Graph the first one on graph is -2x squared plus 8.5x. The less than sign tells me to shade below. Remember to use a dashed line. Then I have 4x minus 2. The greater than sign tells me to shade above. So what I'm looking at is where these two overlap or intersect. That is going to be where my solutions lie.
So again, I graph the two inequalities, I shade the inequalities and see where they overlap, and I remember to use a dashed or solid lines when appropriate. So in this case, I have less than and greater than symbols. I use dashed lines for both because there's no equal sign underneath them. So again, less than I shade below, and it's a dashed line. Greater than, I shade above, and it's a dashed line. Less than or equal to, I shade below, and it's a solid line. And greater than or equal to, I shade above, and it's also a solid line. Using a system to solve an equation. Solve the equation 4x squared plus 3x plus 2 equals 3x plus 8 by writing a linear quadratic system and using the intersection feature of a graphing calculator to solve it. Okay, so step one is I set up my two systems. The equal sign's a great spot to just kind of break those systems in half. So I have y equals 4x squared plus 3x plus 2, and y equals 3x plus 8. From here, I'm going to graph my first equation. Then I graph my second equation. I see where they intersect. So in this case, they intersect at negative 1.22474 and positive 1.22474. You can then substitute those values back in for x and make sure they work and they match with whatever your y value was. Okay, so if I plugged in negative 1.22, I should get approximately 4.3. If I plugged in a positive 1.2, I would get approximately 11.67. Okay. The other way that you can determine whether these equations have two solutions is by setting them equal to each other, just like they were in the original equation, moving all of the terms to the other side, setting it equal to 0, and you can either use completing the square, factoring, or quadratic formula to solve if necessary. So I moved 3x plus 8 to the left side of my equation. I simplified to get 4x squared minus 6 equals 0. I can divide both sides by 4, so I get 6/4 or 1.5. And then I take the square root of both sides, which gives me x equals plus or minus the square root of 1.5, which is 1.22474, which is the same that we saw on our graph. Summary. So when I have linear quadratic systems of equations, I can use either substitution, elimination, or I can graph them to figure out my solutions. So again, when I'm looking at solutions, I'm looking at x equals. So I want that x equals portion. For linear quadratic systems of inequalities, graph the linear and the quadratic inequality and consider whether the graph is solid or dotted, so the line is solid or dotted, and use shading to identify the solution region. Your solutions are all going to be within whatever is shaded by both. There may be cases where you will have no shading crosses, which means there are no solutions to those sets of inequalities. And that is the end of lesson 7.